All right, folks, I just wanted to talk you through the least square regression line with some movable visuals, and I want to talk about the class data set. So I'm going to use myself as an example. My height, 68.5 inches. My hand span, almost 9, but not quite, like 8.75. So I've got first period, third period info. I would calculate my z-score for both. I'm going to have a slightly different relative location. And then just a heads up, the two classes have really, really different correlation coefficients. So make sure you have this information about yourself. First period correlation coefficient, 0.475. Third period, I didn't write it down. All right, third period, I'm going to need your number, but it's definitely strong, which the other class did not have. So that's where I'm at to start with. Now we're going to be adding the information about the line in this video. Just a heads up, the correlation coefficient interpretation is going to be, there is a positive linear, which you get from looking at the graph. We have the graph for first period up here. And then depending on the period, moderate for first period, or strong, like actually in the strong category for third period. So it's fascinating about correlation between height and hand span for students. I don't know if we are representative of only AP students or only students or people of this age in general. We're going to have to figure that out a little bit, but that's where we're at. So next up, we're going to talk about adding a line to the scatter plot that we have, where this was the number describing the strength of the scatter plot, and then everyone has a relative position on there. So what we're doing next is adding a line that's going to help us describe the pattern in general, and help us predict somebody's hand span from their height. Now, I just want to remind you, the scatter plot came first. The line is a theoretical model that we're adding on top. The line is not better. Scatter plot is the origin where all this comes from. And so the line is just a linear line, like basic Algebra 1 business. So if you get stuck sort of in the next couple of days, it's probably Algebra 1 stuff that you want to be remembering. And I just wanted to show you what the line does. So this is our class data set. I haven't figured out how to do this, but a different data set that I have over here just to show you. This is a data set of foot length and height of people. So similar to what we're doing, just feet instead of hands. And then the idea is that I can add a movable line. So if I'm trying to predict a line that sort of describes this pattern, I can try to match the slope. I don't like where this dot is. I'm going to move it so that most of the points are evenly above and below the line. I'm trying to make it through here, so I've described this pattern so I can use it to predict. So this is how the line works. And then the least square regression line, the line that we're working with, what it does is it takes the residuals, which are the vertical distances between every single data point in the line, and it squares them. And then the least square regression line is the line such that as you move the line, the squares add up to the least amount possible. So you notice there's a couple squares here that are difficult. This one's really large. This has a really large residual. So is this one. So I'm trying to balance them so that they add up to the least amount possible. So it's visually, I don't know how good I am at this. I can add the actual correct line on here. Ooh, not bad. So this is saying that I needed to make it flatter. Is that what it's saying? No, the other way. But the least square regression line, that's what it does. It adds up the residuals squared and minimizes them. So that's the line we're looking at. That's how the line is made. We don't need to know that technically, but we need to know it conceptually, right? So same thing here. We have a couple data points that have pretty large residuals. This one's really far below. So somebody who's tall with a small hand span. This is somebody who's moderate height but has a large hand span, in fact, our largest. So again, this line is created so that these points that are far away in particular are not making giant residuals that when you square them are just massive. So the line will definitely take those points into account. Maybe over on this side, there's points above so that this one can be below to balance that out. But this is our equation, and what I can get, so this is Staplet, I can get a visual of how these residuals look, so these vertical distances. So this one's the one with the biggest residual, right? So this is a graph of the residuals for every single height, how far off the prediction was. We're going to be using this to see if we like this model or not. This is a dot plot of all the residuals, so ignoring the height, just what do the residuals look like. The idea is you want this to be normally distributed. This is for way later. And then they give us the correlation coefficient, so that's first period, and this is the equation that we got. So then what I want to do is I want to grab this equation, and I want to describe it, and I want to make sure it's in context. So I'm going to be writing two options. You can write predicted y is negative 4.20 plus 0.176x. You have to define the variables. So right now, before you do anything else, you're going to say, hey, by the way, y hat is predicted handspan. And x is actual height, so they're not predicted. So you can do that. I prefer to do handspan predicted big hat. I do this because I tend to forget to do this, so I'm just forcing myself to make sure it's there before I move on. So this is our equation. So then for yourself, you should be able to get your predicted height. So you'll be substituting. So I'm going to be substituting my height. So my actual height, my point is 68.5, 8.75. So this is my x and this is my y, and I'm currently working on finding my y hat. So I'm going to substitute my actual height into the equation we have. And then we'll see what my residual looks like after that. Now, I happen to know that I have a pretty large handspan. I am a piano player. I'm also a very flexible person. I'm recording. So my predicted handspan and then my next job is to find my residual, which is going to be y minus y hat. So my actual handspan minus what the line said my handspan ought to be based on my height. And the idea with that one is I'm going to have a positive residual. Like I said, I think I have a pretty large handspan for my height. So negative point, so that's 0.89, so I'm going to call it 0.9. So 0.89, So I have a positive 0.89. And what this means is my handspan is 0.9 inches larger than the line predicts. Right? So I have a positive residual. I'm above the line, which means my actual handspan is bigger than what the line says it ought to be. The other way to say the sentence would be that the prediction is 0.89 inches smaller than my actual handspan. The thing I want to make sure to interpret before we move on here, really important, our slope. What does it mean? For every increase in height of 1 inch, handspan tends to increase by 0.1, I'm having trouble with this number, 0.18 inches. This is a very, very concrete sentence, very definitive. I don't want that. I want the wiggle. So for every increase in height of 1 inch, handspan tends to increase by 0.18 inches on average. It doesn't happen for everybody. So the on average is super, super important. So I'm interpreting slope, and we have decided that the y-intercept which is the point 0, negative 4.2, is utter nonsense. This is a person who has no height whatsoever and their hand span's negative 4 inches. We're going to not interpret this because the numbers don't make sense. And the reason they don't make sense is this is extrapolation. We're assuming that the pattern that we see for people from 60 to 75 inches tall is true for 0 inches tall people, and that's just not how it works. I'm going to avoid extrapolation. You do not assume that the pattern continues forever in both directions. It probably changes soon after the edge of your graph. So that's our interpretation of slope, and we are not interpreting the y-intercept. All right, that's where we're at. All right, we're not done. I wanted to walk you through the calculator steps as well. So if you want to retrieve your lists, I'm going to pull up third period actually. So currently I have first period in my list, and then let's say that we're done with that and I've got my equations and I'm good and I've done this problem and I don't need any more. So I'm going to hit on the name of the list, hit clear and then enter. On the name of the list, hit clear and then enter to make it go away. Remember, these are stored, they're fine, you can get them back. And let's say I want to pull up third period. So I'm going to go to second stat, which is list. I'm going to scroll through alphabetically down here and find the thing I need. So I'm looking for height for third period. Oh, you know what, guys? That's not good. So you want to have the cursor on the name of the list. You want to fill the whole list, not just like this first spot. So cursor's on the name of the list. Grab height. Third period this time. I'm saying, yes, please fill list 1 with heights. I want that. Same thing for list 2. So I'm going to put my cursor on list 2. I'm going to go to second stat, which is the list menu, find the hand span for third period, fill those. And then if you want to check the bottom of the list, one easy thing is you can loop up and hit up one more time and it'll go to the bottom of the list. So these are equally long. I haven't made an error. Yay. Now, if I want to get my least square regression line and my residuals, what I do is I go to stat, I calculate. We've already played with this menu, option number 4, linear regression. Least square regression line is a kind of linear regression. List 1 and list 2 is what I'd like to do this on. Now, if you want to keep your equation and not have to type it out, if you go to store regression equation, and if you don't have a menu, you just put the comma next to list 1 and list 2 and put comma and choose this. You want to choose y equals, so you go to variables, so not second vars, but just vars. Go to y variables. We would like to find y1 function, y1, and it's saying, please fill y1 with my equation when you calculate it. I'm going to calculate. It's giving me the equation for third period, which I haven't written down on here yet. So again, third period, much stronger R. This is the equation. It's similar. It's a little flatter on the slope. We have a slightly smaller y-intercept, but that's the equation. And then if you want to go, so you can write it down, make sure to put the hat on there. And if you want to go see it, you want to make sure the plot's on. I'm graphing a scatter plot with list 1 and list 2. I'm going to zoom stat to find it. Just hit number 9. There it is. And if you've chosen y1, it will just put the equation on here. So let me just show you. If you hit just y equals, not second y equals, this is where y1 is. And it just grabbed the equation from linear regression and popped it in here. Or you can just type it in yourself. It's not a big deal. But then the idea is then I have the graph to look at. So I can kind of see people's distances. I can trace. If I'm tracing the dots themselves. So I can see that this person is 73 inches tall and has a hand span of 8. I can see it's below the line. So the line would have over predicted this person's hand span, or rather this person's hand span is smaller than the line predicts. But this is the original data with the line going through, attempting to minimize those residuals, those distances, right? So we're going across the middle. We have about the same amount of points above and below the line. It's not always true. If somebody's really, really far away from the line, we might have more points below to manage to balance that out. All right. Mouse, where are you?